should we, can we get started?
Start and see if there's a natural cutoff point somewhere around 1, so we'll go for lunch and then we see what the afternoon brings.
Maybe 1:15.
Well, most days we've stopped around 1:15 and then get back.
Okay.
I think Professor Moore will be showing up. Professor Moore will be showing up around 1, 1:15 to get us to lunch.
Yeah, but we have to cover 5 lectures, right?
Yeah, as per the schedule.
Yeah. So let's see how it goes.
See how far you come, and otherwise get something else.
Yeah. Okay. Start. Okay. So yeah. So now in this lecture, I'll talk about another electrophoresis technique called isotachophoresis. And I'll abbreviate it as ITP. And we are going to discuss theory and some applications. So the previous lecture we discussed microchip electrophoresis. So understanding microchip electrophoresis is rather easy because the motion of the ions and or you can say the motion of the analyte zones while separation, it's decoupled from the electric field. Okay, only towards the end we saw that if there is a coupling, you can have peak broadening, sharpening, those kind of things. Okay, but ITP is very different. Okay, ITP, the motion of the analyte zones and the local electric field is strongly coupled. Okay, only because of this coupling we get this technique. So it's a bit challenging to understand, but if you are able to get something out of this lecture, I will be happy. The math is bit challenging. I have something on slides, but I'll try to avoid as much as possible so that I can give you some intuitive understanding of how this process works. Otherwise, you need some background in mathematics to understand why you have this kind of nonlinear behavior. So again, just to recap, we are looking at electrokinetic transport. Okay, that is transport of ions and fluid by applying electric field. So again, in this kind of systems, we have a capillary of dimensions, typical width of 10 micrometers, even 100 micrometers. Most of the time we use glass, but we can also use polymers like PMMA or PDMS. And in these experiments, we have electroosmotic flow, but primarily for ITP, we just need to focus on electromigration, because flow is just going to translate everything in the direction of the flow, but electromigration is the main phenomena responsible for the process I am going to discuss in this lecture. Okay. And this slide is crucial. Let's not worry about math and all. I think most of you are from chemistry, analytical chemistry background. I have these on slides, but we can skip it. Okay. So let's recap. Okay, what we have is that if you apply electric field, okay, then the velocity of ions is proportional to electric field. Okay, there are some species which have nonlinear behavior, but let's just use the simplest behavior where the velocity is proportional to electric field, and the proportionality constant is called the electrophoretic mobility. Okay, typical value of electric field that we will apply, the magnitude of electric field will be about 10 kilovolts per meter. That means, for 1 centimeter long channel, you apply a voltage of 100 volts, okay, DC voltage. And typical value of mobility is about, in SI units, is about 3 into 10 to power minus 9. Okay. And that means, if you multiply this mobility with the 10 kilovolts per meter electric field, you will get a velocity of about 300 micrometers per second. Okay, that is the typical velocity that you will see. Now, what we are going to discuss is how we can generate self-sharpening concentration gradients in electrophoresis. If you recall, in capillary zone electrophoresis, we had analyte zones which were moving, but they were also diffusing. Okay? And because of diffusion, the sensitivity was reducing over time. So, can we find a way where we can counter diffusion? Okay? We can stop diffusion, or we can work against the diffusion, so that the zones do not diffuse over time. Okay? The way to do it is using nonlinear effects in electrophoresis, but I will just try to show you a representative simulation, which a visual description of what happens, but let us see how we get sharp gradients in a capillary, okay, in capillary electrophoresis. So, what we do is this. Okay. Let us say that you have a channel, okay, a capillary, you fill it with an electrolyte. Okay. Electrolyte will have negative ions and positive ions. So, let us say that we fill it with sodium chloride. Okay. Although I would not use sodium chloride otherwise, but because it is not buffered, but let us say it is salt mixed in water. Okay. So, you have counter ion is sodium. So, we C denotes counter ion. So, you have sodium is the positive ion, the cation, and the chloride ion is denoted by L over here. Okay. So, you fill it in the channel, but on the left hand side you clean up the inlet and you fill, let us say, sodium acetate. Okay. So, sodium is present, the cation is the same in both the solutions, but here you have chloride ion in the channel and you have, let us say, acetate ion in the reservoir. Okay. Why I have chosen chloride and acetate? Because the chloride ion in absolute terms, it has higher mobility than the acetate ion. Okay. So, let us say L ion is the leading ion, okay, which has higher mobility, T ion is the trailing ion which has lower mobility. Okay. So, now what we do, this is the initial condition. Now, we apply electric field, towards the left hand side, because we want negative ions to move towards the right. Okay. So, what is going to happen? Okay. If you think, okay, in a layman terms, okay, negative ions, chloride ions are going to move towards the right, of course, and acetate ions are also going towards the right. If the electric field were the same in both the zones, then which ion will move faster? Chloride ion. So, chloride ion will move faster and the acetate ions will not be able to catch up, okay, if we think that the electric field is constant, okay, or uniform, but that does not happen. Okay. You can't have a separation of ions in that sense. So, what happens is that the conductivity of the solution behind the chloride ions is going to change in a way that the electric field will increase, okay, behind the chloride ions. So, that electric field times mobility of the trailing ions is going to be same as that of the speed of the trailing ions is going to be same as that of the leading ions. I will show you a video and then that will give a clear picture. Okay. So, imagine that blue ions are the chloride ions, red ions are acetate ions, okay, and I apply electric field. This is just a approximate simulation I have done using imagining them as particles. Okay. So, what do you see? This is the initial concentration of the trailing ions, the red ions, the blue ions are moving towards the right, but this interface has sharpened. Okay. This interface remains sharp. Okay. Let us go back. Okay. Now, let us see. So, I have chloride ions over here, or the leading ions, and I have significantly higher concentration of leading ions over here shown in blue color. I have low concentration of the trailing ions. One example is acetate ions. Now, I apply electric field. Okay. It is not that blue ions are going to move ahead and red ions are not going to catch up and there is some white space in between, that does not happen. Okay. Instead, what happens is that the electric field behind the zone, okay, it changes, the concentration changes, the concentration of the red ions changes, which changes the conductivity of the solution, which changes the electric field, because electric field times conductivity is a constant which is called the current density, okay, the total current divided by the cross sectional area. So, the concentration adapts behind the chloride ions, so that the speed of the chloride ions and the acetate ions remains the same, and this initially diffusive interface between two zones sharpens over time, okay, and remains sharp and just propagates towards the right. So, now let us see how it works. Okay. So, you see that this sharp interface is forming and it is moving towards the right, okay. And if you just look at this interface, the ions, the blue ions moving towards the right and the red ions moving towards the right, they have the same velocity, because if they do not have the same velocity, then the red ions are going to overtake the interface and the blue ions are going to stay back, okay, or go behind this interface, but that does not happen. So, what actually happens is that, okay, the physics governs that you have a sharp interface that forms, the initial concentration of the ions, it changes, okay, and it attains a constant value which depends upon the ion concentrations in the channel, okay, and there is a sharp interface that propagates. Okay. This interface will remain sharp as long as you apply electric field. As soon as you stop electric field, you will have see diffusion of this interface. So, how can you generate this sharp interface? The way to generate sharp interface is to have a high mobility ion filled in the channel ahead of low mobility ion. Okay. Only then you will get this sharp interface. If you have if let us say this T ion has, or the trailing ion has higher mobility than leading ion, it is just going to overtake, okay, the blue ion. So, you will not get a sharp interface. Okay. So, this forms the basis of the separation technique called isotachophoresis, which we call as ITP. Okay. So, the difference between ITP and zone electrophoresis is that in electrophoresis we have a uniform background electrolyte. Here we have a discontinuous electrolyte system. You have a leading electrolyte consisting of high mobility ions initially filled in this channel, and you have low mobility ions in the trailing electrolyte, and you can have a common counter ion, just like in the example I have given. Okay. So, that is what we have to see, that how we can use this kind of sharp self sharpening gradients or interfaces for our advantage for separation and pre-concentration. So, those who are slightly more mathematically inclined, okay, will appreciate that this interface, any interface or any front that sharpens over time, okay, you can think of it as a shock wave. Okay. We know you have some shock waves in aerodynamics. Okay. Similarly, we have shock waves in ions. Okay. These are just interfaces which sharpen over time, they have a self sharpening property. Okay. And why is this self sharpening? Because let us say that the blue ion somehow is kicked to the red zone. Okay. Now, the blue ion is going to see itself in a zone where other ions are moving slower. So, it is going to move ahead. If the red ion gets to the blue zone, it is going to find itself in a zone where all other ions are moving faster. Okay. So, they move at the same speed in their respective zones, not in each other's zones, because the electric field in the red zone is higher than the electric field in the blue zone. Okay. So, this is one interface. This technique or this kind of interfaces we see in a technique called isotachophoresis or ITP. So, the main difference between ITP and electrophoresis is that we use discontinuous electrolyte. So, we have a leading electrolyte which has a high mobility co-ion, okay, and a trailing electrolyte which has low mobility ions, and the counter ion is the same. Okay. For simplicity, we can have the same counter ion. Okay. Now, how we can use this kind of self sharpening gradients for separation and pre-concentration. So, recall what did you see in the previous simulation? Okay, there were two effects. There were two effects. One is this interface is very sharp, it is not diffusing over time. Okay. Other is that this low concentration of the trailing electrolyte is adapting and the concentration is increasing. Okay. Okay. You can think of it as that some system has some memory of what was initially filled in the channel. Okay. So, if you had high initial concentration, whatever ions are displacing the high mobility ions, their concentration is also going to increase or adapt to a higher concentration. This is characteristic of ITP. So, adapting new concentration is proportional to the leading ion concentration and sharp interfaces. These are two characteristics of ITP. So, now let us see how we can do a typical ITP experiment. So, now what we do is that we have a leading electrolyte with high mobility ion, a trailing electrolyte with low mobility ions, and then for electroneutrality we have a counter ion. Now, what we do is, in the previous example we just had this Le and Te, leading electrolyte and trailing electrolyte. Now, initially we dispense some analyte mixture, some sample between the leading and the trailing electrolyte. So, my concentration versus x looks something like this, Le, Te, and initially you have a diffused zone where you have two types of ions. Okay. And now, at this point the voltage is not applied, the circuit is open. Okay. So, now what we do is we apply electric field, we apply voltage. So, what is going to happen? So, we see that you can get sharp interfaces, but what I have done over here is that I have chosen Le and Te in a way that the Le ion mobility, the co-ion mobility is the highest among all the ions over here. The Te ion has lowest among all the ions. S1 sample has higher mobility than S2. So, what happens is when you apply electric field, you will get a picture like this, where you have see there are two effects going on. So, S1 concentration is relatively low over here. It's when S1 displaces the leading ion, its concentration is going to adapt, it is going to increase and becomes proportional to the Le concentration, and these diffusive interfaces are going to become sharp. So, what you get is, if you just ignore this left part, just look at this. So, you have Le and sample. This you have attained a plateau of the sample concentration attains a constant value like we saw in the previous simulation. This interface is very sharp. It is not diffusing over time, it is sharp, it is propagating, it remains sharp as long as we apply electric field. Now, what we have is S2 was in had the sample S2 initially had a relatively low concentration. So, it could not adapt to the maximum concentration. If you have more amount of sample, it would have adapted and attained the maximum concentration that is allowable. And then its zone will start expanding. So, we have two types of zones over here. We have one zone which is of plateau shaped, other is of peak shaped. It depends upon the initial amount of sample that we have, and there is a sharp interface of Te, the trailing electrolyte, with the sample zone. So, as I said, all these boundaries, this boundary, all the boundaries are the boundaries between the adjacent zones are self-sharpening in the nature. Self-sharpening in nature. That means you stop the experiment, you stop the voltage, remove the voltage, it's going to diffuse. You apply again, they are going to become sharper again. Okay. The reason is that as long as you are applying electric field, okay, the high mobility Le ions are always going to lead the trailing ions, and low mobility ions in this case. Okay, for this interface you have leading ion and sample ion, the slower ions are always going to lag behind. But despite having different mobility, the speeds are the same, because electric field, local electric field in the leading zone is lower than the local electric field in the sample zone, and the local electric field in the TE zone is even higher. Okay. So, that the velocity is the same, okay, just because the electric fields are different. Okay. So, the net effect is that you can get purified zones. Okay. You get zones where you just have S1, you just have S2, okay, and these interfaces are sharp. So, as long as you do experiment, you will not have dispersion of these zones. Okay. So, we can just classify, because in certain literature they will just classify in two types. Okay. So, if the initial concentration is high enough, then you will attain the maximum concentration that is allowed. We can call it as a plateau mode, because it looks like a plateau. If the concentration is initial amount of sample is not high, okay, you will just see a peak rather than a plateau, and rather than a broad plateau. Okay. And this distinction just helps when we discuss the way we are going to detect these zones. Okay. So, what do you see in a typical experiment? So, we have imagined that you do not have 2 samples now, let us say you have 10 or 12 samples, okay, 10 and different species in the initial mixture. So, you will have various plateaus, okay, you will have various plateaus, okay, and these zones are migrating. Okay. So, what you can do is, the easiest way is that you put a conductivity sensor at the end. Okay. You can measure the resistivity of the local resistivity of the channel and measure the conductivity as these zones move over that detector. So, you may record a signal something like this. This is resistance versus time. Okay. So, in this particular case, what you are seeing is, you are not seeing peaks. Okay. In electrophoresis, in microchip electrophoresis, in zone electrophoresis, what you detected was peaks, okay, peaks that are separating over time, whose resolution is increasing over time. The difference, the distance between the relative separation between the peaks is increasing over time. Here, the relative separation will not increase over time once the samples have purified. Okay. You will see plateaus, okay, because the leading electrolyte has highest conductivity. So, it has lowest resistivity, local resistivity. The next zone has slightly higher conductivity, slightly lower conductivity, I am sorry, and the resistance is higher. So, you will see a signal like this. Okay. So, like electrophoreogram, you will have an ITP signal, okay, isotachophoreogram. So, based on the plateau heights, okay, you can, in the signal, you can identify which sample do you have. Okay. So, in this particular case, okay, if whether you can distinguish one plateau from the other defines the resolution. Okay. In ITP, okay, the zone width corresponds to sensitivity. Longer the zone width, that means you have more amount of initial sample. Okay. And if you are able to detect a longer zone, okay, that you can correlate it with the initial amount of sample that you have. Okay. And resolution is depends upon how well you can distinguish one plateau zone from the other zone based on the local properties, in this case that is resistivity. Okay. So, the benefit of this process is that you do not have decrease in signal to noise ratio over time. The sensitivity does not decrease, okay, but the resolution is limited. The resolution cannot increase over time. In zone electrophoresis, the peak separation would increase over time as long as you do the experiment, but the sensitivity would go down. Okay. In ITP, the sensitivity will not go down, sensitivity will remain the same over time, but the resolution remains fixed. Once you attain steady separation, you will not see increase in the resolution over time. Okay. So, there is some distortion over here, but we can ignore this. So, why do we want ITP? Okay. So, with ITP, what you can do is, there are two things for ITP you can use for. Okay. One is as a pre-concentration method. Okay. Let us say you want to do capillary electrophoresis and you have a very you have a trace amount of sample in your original mixture. Then what you can do is that you can use ITP to focus the sample in a zone, because the concentration increases over time. Okay. Concentration can concentration is some proportionality constant times the Le concentration. So, the idea is that if you have some charge in the capillary, you are displacing that charge, okay, those ions with other set of ions, those ion concentrations will be proportional to the concentration of ions that you are displacing. So, what happens is that the initial concentration becomes high, okay, and you can use cheap detectors for detection. Okay. And unlike capillary zone electrophoresis, okay, where if you recall in the previous lecture I said that the zones will distort over time. Okay. In this case, the zones are not going to distort, they are going to locally distort, but again because they are self sharpening in nature, as soon as the electric field becomes uniform, the zones will regain their shape and you will get a steady state. Okay. Another point I will come to it later on, is you can devise new ways of detecting these zones using the displacement physics, how these ions behave when you put them in an ITP experiment. I will come to this soon. Okay. So, the key difference is that, okay, from microchip electrophoresis or zone electrophoresis is that the resolution is not going to change over time, okay, but the sensitivity does not decrease over time. So, you can get high sensitivity because the signal will be very high, okay, but the ability to distinguish one zone from the other is not going to increase over time in capillary zone electrophoresis. So, ITP is, I just put a brief background of ITP. So, ITP has been known for quite some time, okay, from 19th century, and it was widely used, okay, for various analytical chemistry applications. But in 2000s, with the advent of microfabrication, it has seen renewed interest for various microchip electrophoresis techniques, and particularly for pre-concentration of samples prior to capillary zone electrophoresis. Okay. So, it is not something very new, it is pretty old, the physics is well understood. So, let me try to explain the physics. Okay. There is some math, but we can ignore if you are not familiar with. So, most of you have chemistry background, is not it? Yes. Yeah. So, let us not go into detail, but some physical understanding, at least the names of the laws that go into describing the physics is essential. Okay. So, because I want to introduce you to this, because we also have to look at my next two lectures are on modeling and simulation. So, we can't do simulations without understanding the equations, right. So, we have to understand a little bit. So, we need to model this phenomena and understand why you get sharp interfaces. Okay. because they defy otherwise our usual observation that you have an interface between two liquids and it will diffuse. So, why is it self sharpening in nature? So, what we do is that let us look at a very simple model of ITP. So, what we say is that we take a small region over here and see how the ion concentrations are changing. So, this is a control volume, a small element over here. The concentration, the rate of change of the amount of ion I, okay, species I, is given by this, okay, and something is you have some mass flux of ions from the left hand side, some mass flux on the right hand side. Okay. So, if you ignore diffusion, the flux is due to the ion velocity times the concentration, that is the mass flux. Okay. So, if you put all of this together, you get an equation, a partial differential equation, which says that the rate of change of concentration is equal to the gradient in the mass flux. Okay. If the more amount leaves than what is coming in, then the concentration has to drop. Okay. Or if more amount enters a small region, okay, than what is leaving, then the concentration is going to increase. So, what you have is, okay, you have equations for the ion concentrations. We have three types of ions for the system shown over there. We have the leading ion, we have the trailing ion and the counter ion. Okay. So, there are three equations. Another condition is, another constraint is that electroneutrality. You can't have unbalanced charges anywhere. Okay. If you have you can say the valences times the concentration of ions, okay, and sum over that has to be 0. Okay. You have to have same number of negative ions as same number of positive ions in a particular region everywhere. Okay. So, another thing is that you put all this together, what you will get is Ohm's law. Okay. Ohm's law just says that if you have high conductivity, then the electric field is going to be low. If you have low local conductivity, electric field is going to be high. And what is conductivity? Conductivity is dependent upon the concentration of ions. If you have more ions, the conductivity is higher. If you have less ions, conductivity is lower. You make more concentrated solution, it has higher conductivity. Okay. You put all together, you get some equations like this. Okay. We will not spend much time, okay. But the main thing is this function, okay, which in analytical chemistry is well known. It is called Colorosh regulating function. So, let me see how to explain if you do not have significant background in mathematics, but essentially you have three governing equations for three types of ions, three species of ions, and you have two algebraic relations. One is the electron neutrality and one is Ohm's law. So, what you can do is that you can work with one equation only, one differential equation, and then you can use Ohm's law and you can use the electroneutrality condition. But what you get is, you get, if you rearrange these equations, just focus at this equation. Okay. It says that this function within the bracket, within the parenthesis, never changes over time. Okay. This is called Colorosh regulating function. It is a function of the valences. So, if you have sodium ion, this Z is +1. If you have chloride ion, this is -1 times the concentration divided by the mobility. If you sum all of them, okay, then this function, okay, value does not change over time. That is what Colorosh regulating function is. Okay. So, the point is this. Okay. So, you fill your capillary or the microchannel with your leading electrolyte, okay, and you will get some value of this function, the Colorosh regulating function KRF. Okay. but when the leading ions are displaced by the trailing ions, okay, this function value remains the same. So, let us see. Okay. So, initially you have the trailing ions over here. Okay. So, the value of this function k in the brackets is this. Okay. You do not have any trailing ions, you have only leading ions. So, valence of the leading ion times the initial concentration of the leading ion divided by mobility plus the valence of the counter ion times concentration of the counter ion divided by its mobility. This is the value of the Colorage function KRF. Okay. But when the sorry, this is when the let us see here. When the trailing ions displace the leading ions, okay, the value should not change. Okay. So, the left hand side of the equation gives the Colorage regulating function value, okay, when you have trailing ions instead of leading ions. Okay. And then you have electron neutrality condition also. So, if you work out, what you get is, you work out the concentration, you see that the trailing ion concentration is proportional to the leading ion concentration. So, practically what it means? Practically it means is that, let us say that I have, let us say 100 millimolar concentration of the leading ion in the capillary, okay, and of the leading ion. At the reservoir in the trailing ion, let us say the concentration is of the trailing ion is 1 millimolar, okay, or very small, let us 100 micromolar, and then you apply electric field, okay, the concentration of the trailing ion is going to increase. It is going to become proportional to that of the leading ion, the ion that is it is displacing, okay, because what this equation on the left hand side says is that this function remains constant. That means, system has some memory that there was some high concentration of ions initially. Now that you are displacing these high concentration ions, your concentration has to increase. Okay. Think like this. So, there is a proportionality constant, but typically this is slightly less than 1, okay, because the mobility of the trailing ion is less than leading ion, but you will see that order of magnitudes of these concentrations are the same. So, the point is that you have TE or you have analyte. Let us say we have done experiments where we start with nanomolar concentrations and we can increase the concentration to millimolars. We can increase the concentration to hundreds of millimolar. So, you can have 1000-fold, million-fold increase in initial concentration. Okay. That does not mean that I am producing more ions. All I am saying is, I have in a bigger zone, I have low concentration of ions, I am compacting them into a smaller zone, so that the concentration is increasing. Okay. So, we can get very high levels of pre-concentration using ITP. Okay. So, what I was trying to say is that if the trailing ion concentration, you can ignore this, okay, trailing ion concentration is lower than the leading ion, then the initial interface it sharpens over time. Okay. This is called a shock wave, okay, in mathematics. Okay. And if the leading ion, okay, has lower mobility, if you have ions in the channel which have lower mobility than the trailing ions, then the trailing ions are going to overtake. So, you will have a dispersed interface. So, that is called an expansion wave in physics. Okay. Is that fine? Okay. So, qualitatively just keep in mind that you need to have high mobility ions in front and low mobility ions behind to get a sharp interface, but if I inject high mobility ions behind low mobility ions, then they are going to overtake. So, the interface will disperse. Okay. That is all. Okay. How it works, okay, qualitatively I have tried to explain. You do not really need to understand the mathematical basis to perform these experiments. Okay. You just need to know that the concentration is going to increase, interface is going to become sharper. Okay. And the point is that, okay, that the speed of the ITP front, okay, is going to be equal to the mobility of the leading ion or the speed of the leading ion in the leading electrolyte zone, okay, in the yellow zone over here, okay, and that speed is actually equal to the speed of the trailing ions, mobility times J by sigma is electric field in the trailing electrolyte zone. The speed is the same, but mobilities are different. And why speed is the same? Because the conductivity, the mu t is less than mu l, but sigma t, which is the conductivity, is lower than sigma l. So, the electric field behind this front increases, so that the speed of the trailing ion becomes the same. Okay. And why does electric field become attains that particular value? Because the concentration adapts to that particular value. So, that is a brief description of the physics of why this sharp interfaces form. Okay. Okay. So, to summarize, what we have is, we have high mobility ions in front, low mobility ions behind. Okay. You apply electric field, you can't have a gap. So, the low mobility ions are also going to move at the same speed as high mobility ions, but their concentration is going to increase behind the low mobility ions and this high mobility ions, and the interface is going to be sharp as long as you apply electric field. Okay. So, whatever I have explained till now, okay, is for strong electrolytes. Okay. Strong electrolytes are, strong electrolyte species are those which are always fully ionized. Let us say sodium chloride, sodium is always in ionized state. Okay. Chloride is in ionized state. Okay. But you may also have weak electrolytes. So, weak electrolytes are those which can partly be in, let us say, weak acids. Okay. So, acetic acid is a weak acid, for example, okay, whose let us say pK is around 5, okay, 4.7 something. So, you can have a species partly in non-ionized state and also in ionized state. So, in practice, the mobility is not a constant. When we talk of mobility in capillary electrophoresis in ITP, it is not a constant. It also depends on the pH of the solution, okay, because if you have, let us say you have a weak acid and you increase the pH, then can you tell me in which direction the equilibrium will shift if you make the solution more basic? Backward or forward? Forward, right? Okay, because if you have more,
H positive will be consumed.
Yeah, H positive will be consumed. So, you will have more fraction of acid in ionic state. Okay. So, if you have a weak acid and you increase the pH of the solution, the mobility, the charge is going to increase, the mobility is also going to increase. Okay. And the opposite happens for basic solution. So, in this way, what we do is that many times we have leading electrolyte and trailing electrolytes, which have the ions may have different mobility, but we can control the pH so that we can maintain their relative mobility. One ion has higher mobility, other has lower mobility. Okay. So, what we need for our final separation is this, okay, that my sample ion should have low mobility than the leading ion. Okay. The trailing ion should have lower mobility than the sample ion, and therefore, it will have lower mobility than the leading ion. Okay. If that happens, that is how you will get separation. Now, to give you an idea, okay, I have done a simulation for you, okay, which will explain how the process evolves, because you are not going to apply field and suddenly you will see separation. It is going to go through a phase, and only after some time you are going to see these plateau and peaks. So, let us look at this simulation. I am showing concentration versus x, that is it is a one dimensional simulation where we are looking at the variation of concentration along the length of the capillary. Okay. I have 100 millimolar of chloride ion in this blue color over here initially. Okay. I have 100 millimolar heaps. Heaps is negatively, it's a weak acid, okay, and I have a counter ion 150 millimolar trace. Trace is a base, okay, with pK around 8 something. Okay. In between the LE leading and the trailing zones, I have put a mixture of 4 analytes. Okay, these acids, these are weak acids. Okay, and then I apply electric field. In which direction should I apply electric field? These are acids. Okay, acid means they once they dissociate, you will get anions. Okay, so anions are going to move towards the positive electrode. So I have to apply. Take positive electrode on the right hand side, apply electric field in this direction, and negative ions are going to move towards the right hand side. Okay. And for this simulation, I have chosen some current density. So, let us see if I am able to show the simulation. Okay. So, once you apply electric field, you see that the faster ions, the faster of these ion is going to move in front. Okay. The ion with lower mobility is going to lag behind, okay, and then they will get ordered into zones of different zones ordered by their mobility. So, you have high mobility ions on the right hand side, low mobility ions on the left hand side, and different zones have only one typically only one analyte. Okay. So, they get purified locally. So, this zone does not have other species. Okay. So, you can purify them, and this interface remains sharp as long as you apply electric field. Okay. So, if you have a complicated geometry, you want to take sample from one side to the other side, you can use ITP for that also. Okay. So, that is how ITP works. Okay. When we look at this picture you will get complete separation only after a particular distance. But once you get complete separation, this whole pattern is just going to migrate. It is not, the zones are not going to diffuse over time. Okay. As long as you apply electric field, they are just going to migrate. So, that is ITP. Okay. You can use it for analysis of small ions in some samples. I will give like some examples today, but in my work we use extensively this for DNA analysis. Okay. How we have done it, I will try to show. But the question is that doing ITP experiment is not easy. Okay. Capillary zone experiment is relatively easy in that sense that you can choose, and all you have to do is you have to choose a background electrolyte. You do not have discontinuous electrolyte, you do not have two electrolytes, you just have one electrolyte. All you have to ensure is that you have the required pH that you need for your samples, and the concentration is high enough that its concentration is greater than the sample concentration. But ITP is all of the the zones are very robust, they are not diffusing over time, but getting the electrolytes in the first place is the main step. Okay. Because all what you have to ensure is that the leading ion has the highest mobility, trailing ion has lowest mobility, because if they do not have high and low mobility than the sample ions, then the sample ions are going to either overtake or trail behind. You will not get this focusing behavior. So, typically this is how this is an easy way to choose electrolytes for ITP. Okay. So, what we do is that there are various types of electrolyte systems. The easiest one is this. Okay. So, what we do is that, let us say for anionic ITP, if we want to separate and pre-concentrate negatively charged species, we take an Le ion which is an ion of a strong acid. So, what we will do is we will use chloride ion. Chloride ion has very high mobility, okay, among highest mobilities of among small ions. Okay. and we use a counter ion which is a weak base. Okay. So, we have a strong acid, okay, and we have a weak base. So, we will have maximum buffering at what concentration ratio? So, if I want to have a buffer, I want to make a buffer, and let us say I put 2 times of 2x concentration of the weak base, let us say 20 millimolars of the weak base and 10 millimolars of the strong acid, what will be the pH? pH will be equal to pKa of the weak base, okay, if you can work out. Okay. That is just a thumb rule. So, you want to make pH 8.1, okay, approximately, which is pKa of trace. You choose, let us say 10 millimolar of HCl and add to it 20 millimolar of trace, and you get pH of 8.1. Okay. Now, what you do is, I want a Te ion, a trailing ion with very low mobility, but it is very difficult to get ions with very low mobility. All small ions have similar order of magnitude of mobilities. Okay. So, what we do is that we choose a Te ion, okay, which is a weak acid, okay, which has pKa which is greater than this value, in this particular case, greater than the pKa of trace, the counter ion. So, what we have is, if I have a weak acid and the pH is not very high, then what I will get is, we will get very low ionization of that acid. So, because you have very small amount of acid in ionized state, the mobility is going to be very, very low. So, you can use that as Te ion. So, let me give an example. Okay. So, what you can do is, when I try to do experiments, I will by default, easiest choices for me is to use chloride ion as the leading ion, because it is fully ionized, it has high mobility. Okay. I will try to see the samples, what kind of pH my samples need. So, let us say you want pH around 7 or 8, you choose the counter ion accordingly. If I need pH about 8, I use trace, and I have 1:2 ratio. So, pH is equal to pK. So, 8. Okay. So, Le is all sorted out. Te ion is what I have to figure out. Okay. So, now what I do is, you see I have various options of Te ions. Okay. So, this is mess, mops, heaps, tricene, and in the brackets I am giving the pKa values of those. Okay. In the rows I am giving the counter ion. So, trace will give you a pH about 8.1. Okay. Is that fine? 8.1. So, what happens is that, let us look at this. Okay. So, if you use trace pH of 8.1 with a weak acid having pK of 6, it will be more or less fully ionized, the mobility will be high. Okay. But as the acid dissociation constant or the pKa value increases, that means you have weaker and weaker acid, the mobility is going to decrease significantly. Okay. So, what we do is, we fix the pH first, and then you choose a weak acid as the Te ion, and then you can tune the mobility. So, that is how we decide the buffers, okay. And then we can detect we can do the experiment, and now we have to do the detection. So, let me show you this experiment. Okay. So, one way is that the ions itself are fluorescent, then we can directly detect them. So, what I am showing you over here is an experiment, okay, where the Le ions are not fluorescent, trailing Te ions are not fluorescent, but I have focused a fluorescent species over here, and you see that the concentration is pretty high. Okay, the signal is good, and it is focused in a very narrow band. Okay. Similarly, in the experiment below, okay, what I have focused is double stranded DNA, okay, which we are visualizing using cyber green. It is an intercalating dye. So, you start with a low concentration of DNA, you can concentrate them in a very narrow zone, but the concentration will increase. Okay. The DNA fragments are not going to get replicated like in PCR, but only thing is we are just focusing them in a narrow zone. So, we can, if the analytes are fluorescent, we can always detect them using fluorescence detection. Okay. What if the analytes are not fluorescent? Okay. Then what can we do? So, there are various ways. One of the methods is that there is an indirect way of fluorescence detection in ITP, because ITP allows you to do this. So, what we do in our experiments is that we put a fluorescent species which does not focus in ITP. Okay. So, let us say that I put a fluorescent species which is even faster than the leading ion. So, what will happen? It's going to overtake all the zones. Okay. But its concentration is going to adapt to the local electric field, okay, because different zones have different electric field. So, the concentration is going to adapt, and that concentration will give you different zones, a different signal in different fluorescent intensity in different zones. So, you can see these plateaus, okay, even though your focused analytes are not fluorescent. Okay. It is an indirect tracer that we have put, which gives us indirect detection. So, let me just put everything together and show you how to do an experiment. Okay. We take a microfluidic device. In this case, you do not need cross chip or anything, you just need a single capillary. Okay. You put your leading electrolyte and the non-focusing tracer, fill the channel. Okay. From this side, you fill your TE, and you can also add the sample in the TE itself. Okay. Then what you do is you apply electric field and you measure fluorescent intensity at a particular location over time. Okay. So, just for general audience, in this case what I did was I just put lemonade in as my sample. Okay. Very small amount of lemonade. So, what I got is, if I did not have this lemonade, I got some signal. Okay. Like this between LE and TE. Okay. Then this is one, LE and TE. Then with lemonade, okay, I got this large plateau, okay, very large plateau. We repeated the experiment 3 times. You see that there is some additional zone that is showing up, okay. And then I spiked the sample with citric acid. So, this zone increases. Okay. So, maybe that is because this zone is of the citrate ion. In this particular experiment, I have chosen Le and Te in a way that only citrate ion focuses. Okay. Okay. But what we did was that we when I was at Stanford University, we worked on a system which was a handheld portable device, where a small microfluidic device would go, and we would use ITP for detection of various toxins and pollutants, environmental pollutants. So, what we would do is that we would use these fluorescence techniques, and the benefit of this ITP compared with electrophoresis is that the device is very simple. All you need is a single channel, okay. And another thing is that the sensitivity is always high, okay. Your sensitivity does not decrease over time. So, it has various applications, okay. We worked for some detection of explosives, okay, and then we looked at some environmental pollutants in river water, and we also just to show that what are the concentration, what are the pre-concentration capabilities of ITP, we can also actually detect picomolar amount of sample. Okay. That is very small amount, low concentration of analytes that can be detected in ITP. Okay. So, let me tell you how much is 1 picomolar. Okay. 1 picomolar is that if you take a grain of salt and you dissolve it in an Olympic size swimming pool, that is the concentration that you get. Okay. And if it is fluorescent species, in ITP, people have shown that you can focus it and detect it, because you can keep on increasing the concentration focus for as long as you want, so that the concentration adapts to the concentration of the leading ion. Okay. So, that is with fluorescence detection, but you can use other methods of detection also. One is conductivity detection. What is conductivity detection? As I said, as the zones move past the detector, if you are measuring the local resistivity, every zone has a different electrical conductivity. So, if you can measure the resistance, then you can measure what is measure the changes in conductivity of the solution as the zones pass by. So, you can measure the signal or resistance versus time like this. Okay. So, one easiest way is that you just poke the electrodes within the solution and measure the conductivity. That is called direct conductivity measurement. Okay. But it has its drawbacks. You are actually your electrodes are touching the solution, and you will also have some electrolysis. So, an alternate way is called capacitively coupled contactless conductivity detection. In this case, you detect the change in capacitance. So, what you do is that, which is related to the conductivity of the solution. So, in this case, the electrodes are patterned outside the channel, they are not in contact with the solution, and by applying AC frequency, you can actually measure the change in the signal and estimate what is the conductivity of the solution within the channel. That is contactless conductivity detection method. But among all these detection methods, fluorescence has the highest sensitivity. Okay. So, let us see how much time we have. Okay. So, how much time do we have? We can.
I suspect Professor Marder will be between 1 and quarter past 1, so.
Okay. So, we can.
15 minutes.
Yeah, 15. Okay. So, now let us look at ways by which we can improve the sensitivity of ITP. Okay. If you recall, okay, how good or how sensitive my detection is depends upon the width of the zones. Okay. Because let us say that the width of this plateau zone is very small, okay, then it is going to be difficult to detect. Okay. So, the longer the zones are, the better it is. Okay. So, that will determine the sensitivity. In this case, the resolution is how well we can distinguish one plateau concentration from the others. Okay. So, we want longer and longer zones, okay, wider and wider zones if we want to improve the sensitivity of detection. So, what we do is that, okay, the easy way to do it is that we use channels which are not straight, but have converging and diverging cross sections. You have a thick channel, okay, merging into a very narrow channel. So, what you do is that if you try to simulate this, this is just for illustration. So, initially you have very narrow zones in the thick channel. The larger cross section channel allows you to load more amount of sample, okay, and when they enter the narrow cross section region, that large amount of sample, the peak concentration does not, the zone concentration cannot increase, right, it is limited by the LE concentration. So, the width of the zone will increase. So, the point is that in the same amount of length, having a large cross section channel in the beginning allows me to load more amount of sample, okay, but I am going to see much wider zones, okay, because okay, for mass conservation, okay, if the cross section is smaller over here, the zones have to broaden. Okay. So, we can do these experiments with this. Okay. Another way to do it is called another way to increase sensitivity is called cascade ITP. Okay. So, cascade ITP is essentially you create a concentration gradient between the leading electrolyte. So, what you do is this, okay, you have initially you have high concentration LE and then you do ITP, but later on you move it to a channel where the concentration is low. So, what happens is high concentration of leading electrolyte allows you to pre-concentrate more amount of sample, but once it goes to the low concentration Le concentration. So, this see initially you get very high concentration plateaus, okay, but the width is smaller, but when it goes to low concentration Le zone, the plateau concentration decreases, but the width increases. So, there is a trade off between the width and the height of these plateau zones. So, the point is that with high concentration leading electrolyte you can load, you can pre-concentrate more amount of sample, okay, and for with low concentration leading electrolyte you can get wider and wider zones. So, people have tried to do this also. Now, what I want to show is that we can now combine what we have studied in both the lectures to our advantage. So, if you recall, what is the benefit of capillary zone electrophoresis? The benefit is that you can improve the resolution as much as you want. Okay, you have longer separation time, higher voltages, and you will have larger and larger distance between the relative separation between the peaks, right. But the drawback over there was that the peak height would decrease over time. Okay. ITP on other hand has very high sensitivity, you can increase the concentration by a million-fold, but the drawback is its resolution is very low. It is very difficult to detect one zone from the other, because the resolution, unlike zone electrophoresis, is not increasing over time. So, the question is, can we combine both of them, okay, so that we take benefit of high sensitivity of ITP and high resolution of separation. Okay. So, this is something I have worked on extensively. So, what we do is that, okay, and I will try to show if I have simulations towards the later part of the day. So, first we take a sample, we do ITP. Okay. Okay. So, what we have done is the initial concentration we have increased. Then what we do is we disrupt ITP. How do we disrupt ITP? We can disrupt ITP by disrupting the conditions which are causing ITP. So, what we do is that, let us say we do focusing of ions, then we add the high mobility ions behind everything, okay, all the focus zones. So, they will disrupt ITP and you will get zone electrophoresis. So, here is an experiment which I had done long time back. So, what I have done is I took a DNA ladder, okay, we focus the DNA ladder in ITP, okay, and you get a very high concentration of DNA starting from very low concentration of DNA. In that case, the concentration of DNA was similar to what you will get from a single cell. Okay. Then we disrupt ITP and you will start seeing various zones, the resolution increases. So, the ITP step helps you increase the sensitivity, the zone electrophoresis step helps you increase the resolution. And recall, if you have a complicated device, okay, a lab on a chip system where you want to do some sample extraction, you want to take sample around some turns and all, then you can use ITP, and once you are at the final stage, then you can disrupt ITP and then you can have separation. So, that is one use of ITP. So, with compared with microchip electrophoresis, which has extremely high separation resolution, ITP is not as such used for separation. Okay, I mean, you can use for separation, but if you have an option, zone electrophoresis is going to give you much higher resolution, but as a pre-concentration step it really helps you improve the detection sensitivity. Okay. And although initially ITP was used for electrophoresis, then people found some innovative ways of using ITP for other purposes as well. Okay. The idea is that you can increase the concentration locally, so we can use it for other things. So, one thing is to enhance some reactions. Okay. So, let me give you one example, which is not about separation of ions. It is more about having reactions and having faster reactions and better detection. So, let us say that you have a DNA strand, okay, and you want to do sequence specific DNA detection. So, let us say a DNA strand has a particular sequence, right, and you want to see whether my sample has that particular DNA strand or not. Okay. For example, this kind of things you can DNA or RNA. Let us say for urinary tract infection, okay, you can take the sample, okay, do the cell lysis, okay, and then you will get RNA, for example, okay, and then you add a molecule, okay, which is called molecular beacon. Okay. Essentially, it is a molecule which binds to one particular strand, one particular sequence of DNA and emits fluorescence. Okay. So, the idea is that if it finds that particular sequence, it emits fluorescence, if not, it will not. Okay. But you see that you need a hybridization reaction between your target and your probe. Okay. And typically, if you do it in, let us say, a 96 well plate, okay, it can take very long time to detect reasonable concentrations of the nucleic acid. It can take a day, for example, for 10 picomolar target. So, what we did was that, okay, we took both of these targets and probe, okay, we focus them in DNA, they have similar mobility. So, they form zones which are overlapping, okay, but imagine that for a reaction, okay, a reaction where you can increase the concentration of the probe and the target, because it is a second order follows second order reaction kinetics. Okay. So, if you increase the concentration, let us say even tenfold of the reactants, two reactants, then your reaction rate increases by a factor of 100, okay, 10, 10, 100. Okay. So, if you can easily we can pre-concentrate samples 100-fold or million-fold, okay, or 10,000-fold, then the reaction becomes very fast. Okay. So, what reaction on normally takes a day, we can do it in seconds. Okay. That is the benefit of pre-concentrating. Again, keeping in mind, we are not replicating, we are not producing new DNA. All we are doing is we are confining them in a narrow zone. Okay. And all this is possible because we are using discontinuous electrolytes. Okay. We are using the self-sharpening physics of ITP, self-sharpening gradients in ITP, so that we can counter diffusion, because if the zones were to diffuse, then the concentration will go down. So, with this introductory lecture, I will on ITP, okay, I will stop here. So, what we have shown is that in ITP you can get self-sharpening concentration gradients, okay, which you can think of as shock waves, which are sharp waves which have a self correcting mechanism, self-sharpening mechanism, that they remain sharp as long as you apply electric field. We have seen how we can do basic ITP experiments, how we can choose electrolyte chemistry, okay, to choose ions, to make the assay with high mobility leading ions and low mobility trailing ions. Quickly, we have also seen how we can increase the detection sensitivity of ITP, okay, and how we can combine ITP and zone electrophoresis to get best of both worlds, get highest sensitivity and the high resolution of zone electrophoresis. And lastly, I have also shown uses of ITP for some other purposes, for enhancing hybridization reactions, but there are various other uses of ITP now. Okay, what people do is another application of ITP is sample purification. So, what you do is that in ITP only those samples ions will focus whose mobilities are sandwiched between mobility of leading and trailing ions. So, if you have let us say a cell lysate and you want to preferentially extract DNA, then what you can do is you can take leading ion and trailing ion such that only DNA or a particular size of DNA has mobility between the leading and the trailing ions. So, when you do ITP you will get focusing only of those DNA strands. Okay. For that you need to choose the leading and the trailing electrolytes carefully. So, that is about ITP. So, remaining part of my lectures will be on how we can do simulations. So, maybe that we can do after lunch. I do not know if you have access to computers, but if you can have computers you can work with me also during the next lectures to do some simulations yourself, because we have very simple tools on internet. You can use those tools to simulate all of these processes that I have discussed. So, with this I will stop. I will be happy to take any questions.
Thank you,
Thank
Doctor, for your nice lectures. And those who have laptop with them, they can bring their laptops and use the simulation tools, and it will be very interesting for you to learn how to calculate the mobile speed and flow of the ions. Right? So we will meet exactly at 2 p.m.
ठीक है.
Thank you.
Okay.